Today we are going to talk about organometallic reagents. Organo, carbon, metallic, metal. It's exactly what it sounds like. It's going to be a carbon thing bonded to a metal covalently. And to give you an idea of why we have these organometallic reagents in our organic chemistry toolbox, I've put in this semi-periodic table thing that I found in my organic chemistry textbook. And as a reminder, electronegativity, which is what this periodic table is showing, is how badly do I want to grab electrons. So I hope you remember by now that a covalent bond is sharing of electrons, but it's not always an equal sharing of electrons. You're going to have maybe one of your elements likes electrons more than the other one. It's kind of like if you have two little kids and one of them's the older sibling, one of them's the younger sibling, and they're splitting a cookie and the older sibling goes, I get the bigger half, right? So elements like maybe nitrogen or oxygen usually are the ones that say I get the bigger half. And so far in our organic chemistry career, when we look at compounds that have carbon, carbon's got a partial positive because if you look at carbon bonded to oxygen, carbon bonded to nitrogen, carbon bonded to bromine, to iodine, etc., there's always going to be a partial positive by carbon because these other elements are so electronegative. Because if you look at the actual periodic table, I mean, it's going to be more real than the one that I have here. Carbon is about there-ish, right? So if we split our table approximately into metals and nonmetals, if carbon's bonded to a nonmetal, it's likely going to be more electronegative as electronegativity goes that way, right? So the purpose of an organometallic reagent is to make a compound where carbon is the one with the delta minus or partial negative charge. So we've got a few different metals that can do that, and they're shown here in this table. Lithium, magnesium, those are super common ones for organometallic reagents, and we can see here this is the purpose of having an organometallic reagent, is so that we can get this bond where carbon is a negatively or partial negatively charged thing. So it's like so partial negative that it's basically a negative charge. We like to think of it and pretend it's like 2 electrons extra and a negative charge. And why would we want that? Well, we want that because then carbon can act like a nucleophile. And if carbon can act like a nucleophile, it can go in and attack another carbon that is partial positive, and we can make a carbon-carbon bond, which is something that we're going to really want to do a lot when we get to something called synthesis. And if you're a bio person like me, synthesis, we know photosynthesis, like ATP synthase, etc., means making things, right? So you're going to get problems where it says like, okay, we're going to start with, I don't know, any starting materials you want that are like only 3 carbons, and you want to make like some crazy big thing. And this has real world applications. Synthesis is used all the time in the pharmaceutical industry. So the point of that whole long spiel that I just gave is that these guys are going to be very good at making new carbon-carbon bonds by being strong nucleophiles. And if you remember, strong nucleophiles kind of do SN2-like reactions. But let's get into it. Let's see what kind of organometallic reagents that we have. Now, I'm kind of making these videos out of order, so I hope that by the time you watch this, I will have also made a video on alkyne reactions. But one of the really common alkyne reactions is, let's say we have something that looks like this. And I know the structure of alkynes can look kind of weird because they're linear, so this is a carbon and that's a carbon, right? And this is what we call a terminal alkyne. So even though this hydrogen I drew looks like an N because I have horrible handwriting, it's supposed to be a hydrogen, so terminal means the end. We've got an alkyne on the end of this compound. And the special thing about that is we can get a base to pluck off that hydrogen and leave some electrons behind and make this a negative carbon just like we want. So for example, one of the things that does this is called sodium amide. It's Na, NH2. Now Na is plus, so NH2 has an electron pair and is minus. And this is just going to act like a base and go over and grab our hydrogen. And our carbon's going to get these extra electrons, so we're going to get something that looks like this. And then as a side product, we're going to get ammonia, but we don't really care about ammonia. Anyways, this is an organometallic reagent because we've got this organo and this metallic, and they're kind of together. And now this, with the partial negative, this is actually kind of a full negative, can go on and attack some partially positive carbon, as nucleophiles do. Well, there's actually a second way to make these guys, and for this one I'm going to try using a different terminal alkyne just to give you an idea of, like, it doesn't matter what's on the other side, as long as we have at least one hydrogen right on that alkyne group that we can attack. And this reagent is called methyl lithium. We can think of lithium like it's positive and this methyl like it's negative. And this electron pair can go in and grab the hydrogen and leave these electrons behind because it's acting like a base. It grabs a proton, the electrons stay behind. And we're going to get this thing, this anion here, carbanion, and it's going to kind of be associated with this lithium. And somewhere else we get CH4 because our CH3 took an H, but we don't really care about the methane. We care about this thing. I've also seen it covalently bonded, so I've seen it looking like this before. It means the same thing because what we tend to do with these metals, and you're going to see this later on in the video, is that when we have a carbon covalently bonded to the metal, we like to pretend that the metal is fully positive and the carbon is fully negative because there's such a difference in electronegativity that that's basically what's going on. So these guys, the name that we give them is acetylides. And this is kind of based on the fact that acetylene is this little 2-carbon triple bond thing, and acetylide would be an anion of that. So we don't really care about the rest of the compound. We only really care about like this little bit here that's going to turn into an anion. So that's acetylides. The next organometallic reagent I want to cover is called a Grignard reagent. So Grignard reagents go by the formula of this. And when we see an R, it's a carbon group, and when we see an X, it's a halogen. So, for example, it could be like methyl here and bromine there. So, in order to make a Grignard reagent, what we're going to do is we're going to start with an alkyl halide. So, for example, if we have this, and we're going to treat it with magnesium in an ether solvent, and I'm going to explain that later. And we're going to make our Grignard reagent. And in our Grignard reagent, we like to think of it, as I've said, we like to think of this whole bit with the metal as positive, and then this is negative because there's such a difference in electronegativity. That's basically what's happening. So now this methyl, which we can kind of just isolate and pretend it's on its own, can act like a nucleophile. We can see our rationale for this down here in this electron density map. So if we start with methyl iodide in the methyl part has basically not a lot of electron density. When we see the blue, this goes by rainbow, so red is lots of electrons and blue and purple is like you have nothing. So that's really partial positive. But when we add the magnesium in, we can see significant improvement. So here it's like more yellowy, orangey. There's more electrons. So in terms of reactivity of Grignard reagents, as far as you need to know, we basically can use any alkyl group out there. The issue comes with what halogen we use. So iodine is the best, then bromine. So we're going up the periodic table, then chlorine, and then fluorine. I mean, fluorine is so bad we basically never see it. We don't want to use alkyl magnesium fluorides for Grignard reagents. We basically never use fluorine in organic chemistry a lot because it's the most electronegative element out there. So it holds onto its electrons so bad and it's so stubborn, it doesn't want to share them with anybody or do anything or make any bonds. So no fluorine. Any of the other guys are basically okay, but if you get asked about the reactivity of the halogens in Grignard reagents, that's the order. So, for example, like if I have a Grignard reagent, like I'm going to continue with my methyl magnesium iodide, and I pretend this is negative and this is positive. If I want to react it with, say, this, then I can just pop this in here via SN2, and we can get that. I don't know if that makes any sense. I kind of drew it weird, but this is this, and this is that. This is here, and here's our new CH3 group. So going back to something I said earlier, why do we want to put this Grignard reaction in ether solvent? Well, there's this whole thing that if you go into the lab and if you make a Grignard reagent and if you use the Grignard reagent, and I've done this in my organic chemistry lab, they use these like gigantic drying things. Like go take like this power dry, it's like a hair dryer but to the extreme, and you're gonna dry all your stuff. Because here's what happens if you put a Grignard reagent in anything with water. So let's take back our methyl magnesium iodide as an example again, and we're going to put it with water. So what we're going to end up getting is one of the hydrogens from water. So I'm actually going to just color code this really quick. One of the hydrogens from water is going to attach to the alkyl group and make it just a plain old alkane or an alk, whatever it was, before it had magnesium or a halogen on it. And then we're going to also have our OH from the water over here. So this is, I mean, it's basically hydrolysis, but it's not bio, it's chem. And we don't want this if we want to use our alkyl group as a nucleophile, because this is going to seriously mess it up. And this goes on not just with water, but with like any alcohol. If it's an alcohol, then this will be an alkyl group instead of a hydrogen. So like if it was like ethanol, that would be an ethyl, but then this would still be an OH. The only place that this is useful is if I have an alkyl halide, let's say that I had ethyl bromide, right? And I wanted to turn it into ethane. Then what I could do is I could treat it with magnesium, and then I could purposefully destroy my Grignard reagent with water, and I would get that plus the side product of HOMgBr. So that is Grignard reagents. The next one I want to go over is called an organolithium reagent. And we kind of saw an organolithium reagent up there with the acetylides, but we're going to go into it in more detail. And I kind of ran out of room, so I pushed my Grignards into where I was planning to do organolithium. So here's an organolithium. It's literally just an organic thing, say methyl bonded to lithium. And the lithium is going to be our positive, and this is going to be negative. In fact, so much so that we don't even use partials. We just like put a plus, and we put an electron pair, and we put a minus. And so you can see in this electron density map that the methyl has got lots and lots of electron density, and so it's going to be a good nucleophile. So how do you make an organolithium reagent? Well, the general formula goes like this. You have an alkyl halide, right? R is alkyl, X is halide. And then you add 2 lithiums. You have to add 2, but you're only going to end up with 1 on your organolithium. Then you're going to get your lithium halide and organolithium reagent, and this is what you want. Similarly to the organolithium reagents, we also have a class of reagents called Gilman reagents. These are otherwise known as lithium dialkyl cuprates. So that's exactly what it sounds like. You've got a lithium, you've got a copper, and you've got 2 alkyl groups. So it's going to look something like this. And the funny thing about Gilman reagents is you can't use both of them. So stoichiometrically, when we're thinking about how much of this do we need versus that for our reaction, we only want 1 lithium dialkyl cuprate, or 1 Gilman, per reaction, because only one of these is going to be able to be used, and the other one's just going to like hang around and do nothing because it's lazy. So how do we make these? Well, this actually comes in 2 steps. So first you want to make, you want to do this twice. So you want to have 2 alkyl halides, and you want to have 4 lithiums, right? Because normally we'd have 1 alkyl halide and 2 lithiums. So this whole thing is just happening twice. And we're going to make 2 of these side products and 2 organolithium reagents. So in order to get a Gilman, you have to first get an organolithium reagent. After that, you're going to have your 2 organolithium reagents, and you're going to add them to something called copper iodide. So this is going to create a side product called lithium iodide, and you're going to get your Gilman reagent. So that R2 is like 2 R groups. I just ran out of space. So that's what a Gilman looks like, and it works exactly the same way. So when you look at this thing, you're going to just pretend this is negative and this is positive and this doesn't exist. That's how you do it. And then you just take like your carbon group and make it act like a nucleophile. So now that we are familiar with some organometallic reagents, let's try some practice problems. So our first practice problem is asking us to predict the product of this ethyl bromide with magnesium in ether. So think about it for a minute. See if you can remember which one this is. Pause the video if you need to. Okay, we're back. Or you never left. So this is a Grignard reagent synthesis. We are making a Grignard reagent out of an alkyl halide of magnesium. So basically the magnesium is just going to pop itself in the middle there, and we're going to get ethyl magnesium bromide. And the reason we do it in ether is because if we did it in water or another like protic solvent, it would get destroyed. All right, let's try number 2. So we have isobutyl iodide. So isobutyl is 1, 2, 3, like that. That's isobutyl iodide. And 2 lithiums in hexane. And the hexane doesn't really matter, it's just a solvent. Okay, what do we think it is? So this one is going to be an organolithium reagent. So we're going to get this and lithium iodide as a side product. And so we can think of this like a minus and this like a plus. And so we really only want to focus on this thing here. And in the next step, this is going to act like our nucleophile. And same thing in this first problem is this is our minus and that's our plus, and this is going to act like our nucleophile in whatever second step. So let's try the next one. So this is 1 bromo, 4-fluorocyclohexane and magnesium. So try to draw out that structure because you should know your IUPAC nomenclature by now. Okay, so I'm going to draw this out. Cyclohexane, 1 bromo, 4 fluoro, and we have magnesium and ether. So hopefully we know this is a Grignard reaction. We're making a Grignard reagent. The problem comes when we see our alkyl halide, it's an alkyl dihalide. We've got 2 halogens. So how the heck do we know which one to react? Are both of them going to react? What the heck is going to happen? Well, I hope you remember that fluorine is awful in organic chemistry. It's so electronegative and so stubborn with its electrons that it doesn't really like to do anything. So it's just going to stay put. And the bromine is going to be where we make our Grignard. So here's our fluorine, stays put, and here's our new Grignard. And our last one, it kind of looks weird. I'm going to try to draw this out in skeletal form. So we have this chlorine, and then like that, and 2 lithiums in ether. What are we going to get? Yep, that's right, an organolithium reagent. So we just replace the chlorine with the lithium, and please don't get fooled or drawn away by the double bond. It's gonna just do the exact same thing, and we don't really care about the double bond. I mean, it could be a freaking benzene if we wanted to, and it would still do the same thing. We would still get an organolithium, organometallic, whatever the heck we're dealing with in that reaction. So I hope these helped. I hope to make another video on how these organometallic reagents work with carbonyl compounds and how they work with alcohols, but for now, know this stuff. You can find more practice problems like this. You can try to make up how to make different organometallic reagents in your head. But now you know what they are, and you won't get confused when you see methyl magnesium bromide or something, and you go, what the heck is magnesium doing in organic reactions? I hope this helped.